Hi everyone, my name is Miss Ellison. I'm one of the maths teachers here at Harris Academy Beckenham, and today I'm going to take you through our maths big question today of why do bees build hexagonal honeycombs? Okay, what you're going to need for this session is 2 different colour pens, okay, A4 paper, a minimum of 1 piece, and some paper to write on. So that could be lined paper or graph paper or anything you like. Okay, so let's get started. First of all, I want you to just think about our big question, why do bees build hexagonal honeycombs, and write down any ideas that you might already know. Okay, at the end or towards the end of this session, we're going to write our new reflections in a different colour and see how much we've learned today. So I'd like you to pause the video, write down what you're thinking, and then we'll come back to that later. Okay, so pause the video now. Okay, so hopefully you've got a few ideas down there, which you're going to add to later, and let's get started. First of all, I want to just address what you already know from primary school, and that is to compare and classify geometric shapes based on their properties and sizes, and find unknown angles in any triangles, quadrilaterals, and regular polygons. You should also be able to recognize angles where they meet at a point, or on a straight line, or are vertically opposite, and find missing angles. So you already know loads coming in from year 6, and it's all stuff we can apply to what we're thinking about today. So what I've got here is the shape we're focusing on, a hexagon. And we're focusing on regular hexagons. And regular shapes, as we know, have equal sides and equal angles. Okay, you should also know that all angles on a point add to make 360 degrees. Okay, that is a full rotation. As you can see here, if you were to check for me, 87, 53, 80, and 140 should add up to make 360. Okay, and we can use that to find missing angles. So those 2 things are really going to help you today with discovering why do bees use hexagonal honeycombs. Okay, so what we've got here is myself making a hexagonal table almost. And what we're going to do is we're going to make at least 3 of these so we can fit these together and see a tessellation in real life. Okay, so I'm going to talk through it as it's going on. You can pause this video whenever you like, rewind whenever you like, so you can get it right. Okay, I made about 10 of these today, and I'm going to show you that they all make this lovely big honeycomb. You can make as many as you like, it's up to you. Okay, the bigger the better. So let's play this video. 2 seconds. Okay, just going to turn the volume down and let's play. So I've got my A4 sheet here, and what I want to do first is split this into 4 equal pieces. So I'm folding it in half, okay, nice and straight, nice and accurate. And you can use a pair of scissors, but I like to use a ruler, okay, because I think the ruler just makes a straighter edge, obviously, because it's a ruler. So I place the ruler at my crease and I rip that down nice and firmly. Okay, so I've got it in 2 separate pieces now. Okay, I then halve this piece as well to get my quarters. Okay, quarters here is going to make 4 hexagonal tables. Okay, so that is going to be plenty. We want at least 3. If you want to make more, you absolutely can. Okay, I've done some in green, I've done some in blue, and I've done some in yellow, which we will see later on. So I'm just finishing off my quarters here. Pause the video at this point if you need extra time to do it. If you're using scissors, it probably won't be as quick, so pause and play as you see fit. So I've got all 4 sheets here, okay, ready to go. So grab one of those and you're going to fold that in half to make a crease in the middle, like this. I might even have to pause it myself. Okay, you're then going to get the bottom right corner and you want it to join that middle line and the bottom left corner. Okay, you want the corner to join the middle and you want to be a nice sharp point at that left corner there. And a really good crease. Okay, and I'll pause to show you what it looks like. There you go. So it's touching the corner and the bottom left corner is nice and sharp. Okay. The next step, you're then going to essentially make a triangle. You want that line to join up with that crease that you've just made to make a nice triangle. You will have a bit coming off at the edge here, but we're going to sort that out now, as you can see. Okay, we are going to flip that over, and that little excess bit on the top there, we're going to fold that in, so we've got a lovely equilateral triangle. Then to make it lovely and neat, we're going to tuck that underneath so we do not see that in our way. Okay. So from this point, I want you to get the corner and join it up with the other corner, like so. Make a nice crease in the middle, and the reason we're making these creases, I'm just going to pause here. Okay, the reason we're making these creases is because we're going to get the exact center so we can make an exact hexagon, so all of our angles are perfect. The next bit is where it gets a little bit more difficult, so watch nice and carefully. From this point, you're going to lift up that excess bit, take the bit in the middle out, and we want to place that on top. Okay, and this is going to make our center point, where all those creases line up in the middle, where my fingernail is there. Okay, take each corner of our triangle and place that in the middle, fold towards that center point. This is going to make our perfect hexagon. Okay, and can we see it form now? And these three little points here are going to make our essentially our table. Okay, so it's going to stand up nice and neat like that. Okay, and I've got a few that I made earlier, which I'm just going to add to this, and we're going to see how they fit perfectly tessellating. Now we're going to discover why do these tessellate and what size these angles are, and maybe what other shapes could tessellate. What makes a hexagon so special? You can see I made absolutely loads today, just so I can show you what it would look like as a full honeycomb structure. And once you've made about 2 or 3 of these, it gets really easy and you don't need the instructions anymore. So make as many as you like. But I wanted at least 3 so you could see how they fit together at a point. And remember, all angles on a point add to make 360, and that's a really key point. Okay, so hopefully you've got your honeycomb made now, just like the bees would. Okay, and we're going to reflect on this. I'm going to ask you a few questions, ask you to pause, think about it, and then I'm going to talk through what the answers would be. So we've got, what is tessellation? Okay, I have said the word tessellation quite a lot, but we're going to define that. What angles are present in a hexagon? How can we identify what shapes will tessellate? Why do bees use tessellating shapes, and why do they not use circles? What impact does this have on the bees' productivity? Okay, and when I'm going through these questions, I want you to add in a different colour to your spider diagram from the start, okay, so we can see how much we've learned. And there's a challenge for you there. What are the polygons tessellate, and can you create them? Can you create that tessellating structure like we did with our honeycomb? Okay, it's not easy, and you might have to get your protractor out. Okay, so that's a really nice challenge for you if you want to continue doing that. So let's have a little look. I want you to first pause, have a little think about these yourself, and then once you've had a little think and maybe added to your spider diagram, you can play and I will discuss with you. So what is tessellation? The definition is the process or art of tessellating a surface, or the state of being tessellated. An arrangement of shapes that closely fit together, especially of polygons, in a repeated pattern without gaps or overlapping. The key point there is there are no gaps and no overlapping. How could this be useful to the bees? How did they know? What angles are present in a hexagon? Okay, so we've got here our, whoops, let me get the pen. Okay, we've got our 120 degrees here, and a regular polygon, remember, all of these angles here are 120. Now, look at your honeycomb structure. How many hexagons are always touching each other at a point? Okay, I'm going to draw them in. It was like this. Okay, so we've got 120, and we've got 120 and 120. All angles on a point we know add to make 360. All of those add to make 360. So what do you think is the key feature that makes regular polygons tessellate? Can you think of any other regular polygon where all of the angles meet at 360 degrees? Have a think about it. Try and draw it. Okay, so why do bees use a tessellating shape? Why do they not use circles? Let's have a little look. If I was to draw circles like this, what is wrong with that? How is this going to impact bees' productivity? In order to make these structures, they have to make beeswax, and that can't be easy to make. So they want to be making the minimum amount to maximize how much honey they can hold in it. Okay? If I've got these circles, what's going on in these areas? Absolutely nothing. They're useless. All these gaps are useless. So we need a tessellating shape to make sure that we've got the most efficient structure. Okay? The less beeswax they have to make, the more productive they're being. So circles would be a no-no. Okay? Could you think of any other shapes which perhaps might work? And why would the hexagon be more efficient? Why would triangles not be more efficient? They tessellate. So why would they not be the most efficient? Let's have a think about it. How can we identify what shapes will tessellate? We touched on it earlier. All angles at a point add to make 360. That's why if I've got triangles, you'll have to excuse me, I'm using my finger. I haven't got a pen. It's run out of battery, of course. But we've got triangles there. What are the angles in an equilateral triangle? Okay, we know all angles in a triangle add to make 180, and an equilateral means they're all the same. So each of them is 60. And how many triangles have I got here? 1, 2, 3, 4, 5, 6. And we know that 6 times by 60 equals 360. So is that going to tessellate? It is. Okay, so think about it. Are there any other shapes? You can see here, these aren't regular polygons. It almost looks like a lot of cubes put together. Okay, try and get really inventive with it. Try and draw a really, really lovely tessellation, something you'd want on your bathroom tiles. What can you think of? Okay. In summary, we've learned a lot here. Hopefully you've been adding. I'm just going to go back here. Make sure that you've been adding to your spider diagram. How many more things have you got since we first started? Okay. Do you think you understand why the bees use hexagons? Okay, I've got a really nice video to show you, but before we do that, I want you to come to your own conclusion. I want you to reduce everything that we have learned in this lesson, everything we've spoken about, into 3 key points. What has really stood out for you? Okay, make sure to link these to maths, obviously. Okay, link it to your angles, link it to tessellation. Okay, why do you think bees instinctively knew that hexagons were going to be the best to do the job? Okay, math is in nature everywhere. Okay, you've just got to look for it. So 3 points. Okay, pause the video, write what you think is the most important thing that you've taken from this, and also use a diagram. I'm all about using a diagram to illustrate your point. Show me what angle you're talking about. How big is that angle? Use numbers. Okay, so pause the video and then come back when you are done. Okay. So my favourite physicist, Brian Cox, he's done a video just on this, and what is called the honeycomb conjecture is a problem that mathematicians have been trying to solve for thousands of years, and they've been trying to figure out why are hexagons the most efficient shape. Thousands of years they've been trying to figure it out, and just recently they've proven it. Okay, so just watch this video, and then there's a little link there at the bottom if you wanted to continue some research on this. Okay, so we're just going to watch this together.
It's actually a mathematical question. Problem is, how do I divide up a volume into shapes of equal size using the minimum amount of stuff? Now, why does that matter to a bee? Because that stuff is wax, and wax is extremely valuable to the bees. So what shape should it be? Should it be squares, or should it be triangles? You can see it can't be circles, because circles, when you pack them together, leave gaps, so they're not very efficient. Or could it be that hexagons are the most efficient? Well, that is actually a simple sounding question with a very complicated answer. It's one of the oldest questions in mathematics. It's got a name, actually. It's called the honeycomb conjecture. Mathematicians have worked on it for thousands and thousands of years, and it's only recently that the honeycomb conjecture was proved. Here's one of the proofs. A huge paper, pages and pages of complex mathematics. And it turns out that hexagon is the most efficient shape. The bees knew what human mathematicians didn't know for thousands of years. Actually, I'm using know in quite a loose sense there. There's still a great deal of debate amongst biologists as to how the bees actually do it. Do they build hexagons from scratch using some kind of instinctive behaviour, or do they in fact build a simpler shape, perhaps circles, and then because the wax heats up it can deform and the laws of physics themselves change the circles into hexagons? That's still not agreed upon, but what is agreed upon by the mathematicians and the bees is the hexagon is the most efficient shape. That just shows you it's a beautiful thing. Mathematics is the universal language, and when you look at a perfect honeycomb you see a shadow of that language of mathematics made real by bees.
There was a key point there that you just said, that mathematics is the universal language, and it's something that I say to my students all the time. It doesn't matter where you go in the world, you know, there's going to be someone there. We all model the universe and the world in the same way with numbers. So it's such a special subject, and I really can't wait to see how you guys get on with maths, and we all really look forward to seeing you in September. I hope you enjoyed this, and I hope you sort of opened your eyes to what might be out there in the world in terms of maths. And you know, when you're out in nature, spot those sequences happening, spot all these little things, all those patterns. You know, maths is all about patterns, so maths is everywhere. You just got to look for it, and we look forward to seeing you in September. Thank you.